Section 11.7, angular momentum of a rigid body. So no longer just a particle flying through space, but an actual full-sized object. So we'll sum the angular momentum of the particles to find the angular momentum of a system of particles, which you can imagine if you have some object, right, that you could treat each of the parts of this pen as particles that have some angular momentum. So we could sum up for the total angular momentum, we'll use a capital L, and that's equal to the individual angular momenta of each of those particles for the full summation. And so then the rate of change of the net angular momentum will be equal to the summation of all of the torques that are acting on all of the parts of our object. In other words, our net torque is defined by this change in angular momentum, that the net external torque acting on a system of particles is equal to the time rate of change of the system's total angular momentum, L. So note that the torque and the angular momentum have to be measured relative to the same origin. And if the center of mass is accelerating, the origin must be that center of mass. So that fixes you in that you have to use that as your center of mass in particular. So this tells us that, hey, if we want to increase or decrease the angular momentum of a system, we need to apply a torque in order to do so. We can find the angular momentum of a rigid body, again through summation, summing up all of the angular momenta of the individual particles, the pieces that make it up, and so noting that each of them have a mass and a velocity and a radius out to that particle. But if we rewrite the velocity, the linear velocity, in terms of angular velocity times r, angular velocity on something that's rotating is the same for any point on the body. So that can actually come outside of the summation. And what we're left with is a summation of mass elements times their distance from the center of mass. mr squared. We've seen mr squared before, right? Yeah, for particles, that's their rotational inertia. So this sum of all of the rotational inertia of all the parts of the body is just the total rotational inertia I of that object. So we can rewrite our equation to then be that it is L is equal to I times the angular velocity. This is a really useful way to calculate angular momentum. Anytime you don't have just particles flying around, this is the one you want to keep in mind. I omega, I omega. It just pops up again and again. So it's a great equation. Hang on to that one. And with that, we have another table of corresponding variables and relations for translational versus rotational motion. So translational force, our rotational equivalent is torque, which we can calculate with r crossed with F. Linear momentum, we have angular momentum, which we can calculate with r crossed with P. Linear momentum total, capital P, is the sum of all the individual ones, same for angular momentum. The total linear momentum of the system is the total mass times the center of mass velocity. For angular momentum is the rotational inertia times the angular velocity. And then Newton's second law, the net force or net torque is equal to the change in momentum with respect to time. And this is a bit of a spoiler. Next section, we will see a conservation law with our angular momentum, in which the angular momentum will stay constant given certain conditions. So closed isolated system, it tells us in that. So that is coming. That should be good to see. Before we get there, we have one more checkpoint to do in this section. So checkpoint 6, in the figure, a disk, hoop, and solid sphere are made to spin about a fixed central axis, like a top, by means of strings wrapped around them, with the strings producing the same constant tangential force F on all three objects. The three objects have the same mass and radius, and they are initially stationary. Rank the objects according to A, their angular momentum about their central axes, and B, their angular speed, greatest first when the strings have been pulled for a certain time t. So I want you to think about this for each of them. And if it helps you, I threw in this slide from chapter 10 on calculating the rotational inertia. This is table 10-2, some rotational inertias for different objects. So you're welcome to take a look at that. You can pause your screen here if you want to look, or you can go back here to the original problem statement and pause here. So either one, but either way, go ahead and make sure to hit pause. Okay, I'm trusting you did that. Let's see, so the first part is finding their angular momentum about the central axes. Angular momentum, we saw that the dl dt, the change in angular momentum, is going to be equal to the net external torque. So what's applying an external torque on these objects? Well, it's this external constant tangential force F that's acting on them. And it says it's the same force on all of them and that they have the same radius. So if it's the same force in the same direction with the same distance, each object has the same torque acting on it. If it has the same net external torque acting on it, it has to have the same angular momentum. Because that's the only thing creating angular momentum is this external torque. What will be different is the angular speed, given the fact that these are different shapes with different rotational inertias. So as we look at the rotational inertias, the hoop has the largest rotational inertia, I is equal to mr squared, because all of the mass is at the edges, so it's the hardest to get it rotating. Versus we have the solid sphere is 2/5 mr squared, and then the disk, which it mentions, let's see, we want to keep it straight. We have two disks here, right? We have one about the central axis, and then one about the central diameter. So central diameter would be spinning around like so. Central axis would be more like a rolling. So it would be the 1/2 mr squared versus the solid sphere is 2/5 mr squared. So the solid sphere, because it cuts some corners, is able to have a slightly lower rotational inertia. Because it has the lowest rotational inertia of the three, what we see is the sphere does have the greatest angular speed. Why? Well, if they all have the same angular momentum L, but if our angular momentum is equal to the rotational inertia I times the angular speed, then if you're able to reduce your rotational inertia, then you will have a larger angular velocity. So the sphere has the least rotational inertia, the largest speed, versus the hoop has the largest amount of rotational inertia and thus the smallest angular velocity, even though all of them do in fact have the exact same angular momentum, since they have the net external torque that is the same for each of them. So that pulls us through section 11.7.